Well, hi again, and welcome to Lecture 2 of Physics 2114, Term 2, 2020. So in this lecture, we're going to continue with our review of Physics 1b that we started in Lecture 1. In Lecture 1, we discussed the electrostatics component of the first half of Physics 1b that you had either recently in Term 1 or perhaps last year, or maybe at some other place. I just wanted to first finish up the electrostatics part and mention dielectrics, because this is something we will discuss in detail in a bit more of a general and technical vector calculus way in this course. So if you remember, with dielectrics, you may have considered a situation when you have a dielectric contained between, say, two plates of a parallel plate, two conductors forming a parallel plate capacitor. And in this situation, if you apply a voltage across the plates, you get an electric field. And if the dielectric were absent, you would have just this electric field E0 here. Of course, with a dielectric, the dipoles align. So their dipole moment is parallel to the field, and remember that each dipole had this small p dipole moment. And when they align, when you have very, very many of them aligning with the field, they create their own field over here, E prime, which is counter to the field E0 that would be there if there were no dielectric. Now remember, typically dielectric materials, these dipoles are atomic, so this cartoon is very, very rough. You know, it's in reality, these dipoles are very, very, very tiny compared to the size of the system. And so the contributions of the electric fields of all the dipoles we can think of as being continuous and uniform, as in this diagram here on the right. And the effect of this means that there are polarization charges that build up at the surface of this dielectric, and we can think of as these polarization charges as creating this field E prime that cancels out part of the original field, and the resulting field E here is much, much reduced compared to the case of no dielectric or free space in between these plates. So in the end, in a dielectric, in this simple situation, we have the magnitude electric field E0 divided by K, or kappa, let's call it. Kappa is this constant, and we call it the dielectric constant, or we called it in Physics 1b, we called it the dielectric constant. And we knew that it had to be greater than 1. And in other words, it's if, in this situation at least, it's if in the dielectric that our permeability epsilon naught gets replaced by kappa times epsilon naught, which in Physics 1b we called epsilon. And of course, again, kappa is greater than 1. Now in Physics 1b, we typically considered some very simple situations where this was possible. In Physics 2114, we'll approach this problem from a much more general perspective. We'll see that we can write a polarization field. It will be a capital P, and it will be the polarization, or it will be the dipole moment per unit volume. And we'll see how that gets associated with polarization charges depending on this capital P field that we'll introduce later in the course. And we'll see that it's not always that this holds. The situation is actually much more complex. But that's what we'll do later in this course. Anyway, it's good to understand the simple picture before we jump into something more complicated, which again is why we're going through this review of Physics 1b. Now, if you had my course for Physics 1b, you would have we would have done this, or you would have seen this problem that we did in my class, where we assumed again a dielectric sandwiched between two parallel plates of a capacitor, and we actually found a relationship we used Gauss's law to actually find a relationship between the dielectric constant and this induced polarization charge. And we did this for this simple example. We drew a Gaussian surface, and I'm not going to go through this in detail, but I'll let you go through it on this slide on your own time, and you can read the notes. If you have the notes from 1B, you can look at those again. But we mentioned that the charge on the conducting plates is said to be free charge because it can move if we change this potential difference between the two plates. And we wrote some equations for using Gauss's law. This is just using Gauss's law, and we use these equations to relate, and we were able to derive some equations to relate the induced charge Q prime, the so-called polarization charge. So like I said, in this course we'll see that we can generalize this, and we'll find that whenever we have a dielectric, that we'll get a polarization field that describes our dielectric and the microscopic dipoles. And once we have that polarization field, we'll be able to, for example, calculate this polarization charges in a much more general sense. Okay, let's move on then from electrostatics to what we call magnetostatics. And magnetostatics are simply, of course, to have magnetic fields we need charges in motion, but we imagine that we're in some sort of steady state, that is, we have steady currents, and then that's why we use the term magnetostatics. So it's whenever we have steady currents or charges moving with uniform velocity. So if you remember, let's go back to 1B. We remember that we started with electrostatic force, but it was discovered that for charges in motion, there's an additional force that depends not only where the charges are located, as in for Coulomb's law here, but how they're moving. And this magnetic force between two moving particles, here we have the force between some charge Q1 and Q, where Q1 is moving with velocity V1 here, which is a vector, and Q is moving with V, and it looks very, very complicated because of these cross products. The force is proportional to this constant mu naught over 4 pi, and this mu naught has this exact value, and we described why this value was exact in physics 1B. We'll see that in just a minute. Well, just like we did for electrostatic forces, we can use this idea of a test charge to define the magnetic field B, and then we can write the magnetic force on some charge Q is given by the cross product of its velocity times the cross product with the magnetic field times the charge. And this magnetic field can arise from other charges in motion. So for this really simple problem, we can immediately write down the magnetic field created by one single charge moving with velocity v1. Now, we'll call this a magnetic field B. If you look in other textbooks, especially older textbooks, they will call this B field the magnetic induction, and they'll call a field that H that we'll get later the magnetic field. We'll call H. We'll use the notation of the textbook Griffith, so we'll call magnetic field. We'll call B magnetic field, and when we get to this field, you'll see that will be called H. We'll call that the auxiliary field, but that's later in the course. So we have magnetic forces on charged particles, and the really simple example, well, in all cases, the magnetic field generates a force perpendicular to this field direction and the velocity of a charge. That's just what this cross product is. Of course, the resultant vector of a cross product is perpendicular to both the vectors involved. And so immediately you can see if you have a situation where you have a uniform B field, in this example on the right pointing into the plane of the screen, and we have a charge in motion with an initial velocity perpendicular to this magnetic field that, and this magnetic field is uniform, the force will always, of course, be perpendicular to the field and the velocity, and that means it will always point, for example, in this direction when the charge is here, and that will cause the charge to move in a circular motion. So the motion of a charged particle in a magnetic field is circular, and in this situation, and the magnetic field then provides a type of centripetal acceleration. And so you can, if you want, you can actually derive the so-called cyclotron formula, which relates the magnetic field and the velocity to the radius of curvature of this motion in this plane. And of course, we discussed in 1B the interesting experiment that was performed by J.J. Thomson, where he used crossed electric and magnetic fields. So he had a region where he had electric fields and magnetic fields, which were tuned so that the particle suffered no deflection. And then as the particle passed into this other area where there was only a magnetic field, essentially, you would see a deflection. And using the cyclotron formula, you could actually what Thomson could do was actually figure out the so-called ratio of charge to mass, and he discovered that, well, he was expecting H plus ions that are protons, and he found another particle that had a much larger Q over m because the mass of electrons is much smaller, and that's how he discovered, of course, the electron. And of course, this type of cross DNB fields are known as a Wien filter, and that's how some mass spectrometers work. We also showed in Physics 1B, we also discussed the Hall effect, which is very, very similar. I won't go through that. You can look at this slide on your own time and recall back in Physics 1B how you could use, by passing a current through a strip oriented in a perpendicular magnetic field, a potential difference would build up. And in the steady state, you could use this effect to actually determine the carrier density and also the sign of the charge of the carriers. This sort of Hall effect is used even now to do similar these types of measurements. But it's basically all follows from the combination of electrostatic and magnetic forces, just like the experiment of J.J. Thomson. Very similar to the experiment of J.J. Thomson. Okay, well, once we understand that we have forces on moving charges, that is, forces moving through a magnetic field B, will have a force that depends upon their velocity, so it's perpendicular to their velocity and the magnetic field, then it's quite easy to understand that if we have wires carrying currents, that we'll have forces on those wires. And we will consider steady currents. That is, we mean the current is not piling up or spreading out anywhere. It's the same at all points in the wire. And the simple example here is to consider a straight segment of wire, as in this diagram. And you can see that having a steady current is equivalent to having a uniformly charged, let's say, rod that's moving by at some uniform velocity v. And if this rod was uniformly charged, that means it has a linear charge density lambda. We would have this relation that the current I times this vector L is a unit vector that points in the direction of this straight piece of wire here. Then I times this unit vector L will be the charge density times the velocity. Right? And you can check that the units of this match. Now, and here we've actually used this unit vector L, which just points in the direction of this piece of wire to keep track of the direction. So if we look at a if we look at a segment of this wire here that has length L, it has a total charge lambda times L. And if we use this equation for the force on moving charges, then we just plug this Q here into this formula, and we'll see that we'll have a force on the wire that's I times this vector L, which has direction in the direction of the current through the wire, and it has magnitude L, which is the length of the wire, across with B. Okay, so we see now how to calculate the force on a straight segment of wire. That's very easy to generalize. Suppose now we have a wire that has different a set of different segments. Then of course we would just sum the forces together. And in fact, by now you should be able to see that we could calculate the force on some arbitrarily shaped wire in a magnetic field using integral calculus. And the way we would do that is we would have some arbitrary wire. We would break it into a bunch of segments. So this would become something like DL, and on this side DF. And if we take the limit such that we get an integral, then we just sum up all the contributions, and we could handle the force on some arbitrary current-carrying wire. Well, we derive the force on a current-carrying wire. That is a wire that sits in a magnetic field. What about the opposite situation? Suppose we have a wire that's carrying some current, and we're interested in the force on some moving charge or other wire out here at point P. How do we handle that situation? I mean, a current-carrying wire has moving charges, so we could also take the point of view that the moving charges in this wire produce a magnetic field. And let's calculate that. Well, for this kind of problem, the magnetic field of a steady line current element, that is some small piece of the wire, is given by this so-called Biot-Savart law. There's nothing mysterious about this law. It really just comes from this Lorentz magnetic force written such that the charge and times velocity has this form as we had before in our earlier example. So this just tells us how to calculate the contributions from this dl, little l vector of the magnetic field and how to sum those up. That's all this does. So you can see here the details. Right? And in Physics 1B we did a bunch of examples to get used to this Biot-Savart law. So for example, one of the simple ones we did, which is very, very relevant, of course, is to find the magnetic field at some distance s here from a really thin wire carrying some current I. And I'll very quickly go through the details here because you definitely had this in Physics 1B, but you can make some arguments about symmetry and fields that cancel, and you will know right away you will realize that the B field has to be completely tangential here just by using the cross product. And if you want to directly calculate it, then you use Biot-Savart law. And here I've done the integral using theta. You could also integrate using this distance here. The trick, of course, is just to, which you should have gotten some experience with in first year physics, is to set up a proper integral so you can actually do this. And what we found, of course, was that the magnetic field from a current-carrying wire, a very straight, long wire, or a wire that we're very close to, had this form. The magnetic field made concentric circles, and the magnitude fell off like 1 over the distance from the wire. Hope you remember that. And if you don't remember it, go back and look at your notes and make sure you understand how we derived that, did this calculation directly. So this is the kind of analogous version to calculating the electric field by knowing a charge distribution. Here we're calculating the magnetic field by looking at the small elements, small current elements that make up our wire. And with electrostatics, we saw that in very symmetric situations, we could use Gauss's law to very conveniently calculate electric fields for very symmetric situations. And we have the same thing for magnetic fields, and you learned that in Physics 1b, and that's known as Ampere's law. And basically, Ampere's law was kind of analogous to Gauss's law, and it told us that if we consider the line integral of the dot product of the magnetic field times this element of our line integral, this integral, this value of this line integral would be equal to mu naught times the enclosed current. Now, it's really interesting because in a couple of lectures, we'll actually see how we can write Gauss's law and Ampere's law using differential calculus, notation of differential calculus, and these will actually turn out to be so-called two of Maxwell's equations. But anyway, from 1b, you should remember Ampere's law and how to use it. So, for example, we'll do this problem again where we consider the magnetic field produced by a long straight wire carrying some current I. And so, without even doing a calculation, you can deduce that the magnetic field has to be tangential. That is, it can only have a component in this so-called phi direction if we use cylindrical coordinates. Well, how do we know this? Well, from symmetry, it can't depend on this angle because we're considering a long straight wire carrying current in this direction. So it has to be independent of phi, this variable. And if we consider any point P, then the contribution from every point dl vector on this wire is going to be the same direction given by this cross product, right? And so all the contributions will have the same direction that you can see from the cross product, right? And so that means that, in other words, if this is our wire, we're looking sort of at the wire from this direction here. We're going to be summing up. If we used Biot-Savart Law, we found that we would sum up these contributions, and each contribution is going to give a piece of this form that involves the cross product of this vector with the B field, and so that means that all the contributions at this point are all going to be pointing out of the plane, as in this picture. Okay. And so in this case then, Ampere's law, so we know, what do we know? Before we did any calculation, we knew that the magnetic field could not depend upon phi, so it has constant magnitude as we go around, and it's always tangential, and so that allows us very quickly to do this integral without thinking too much about it. It's just the circumference, 2 pi s times the magnitude of the B field, and this allows us, again, to solve for the magnetic field. Anyway, that's what you learned in Physics 1b. And of course, another example, we could use Ampere's law to find the field inside a long cylindrical conductor. To do this, we once again considered a circular Amperian loop of radius r, but we could actually handle the case that r is little r, which is the radius of our Amperian loop, is smaller than capital R, which is the radius of the wire. And if we assume that the current is uniformly distributed, then it's very easy to calculate the enclosed current, and it's very easy then to use Ampere's law, and we could find that the current builds up linearly while we're inside the wire, and then it falls off as 1 over R outside the wire as for the long thin wire. Of course, that's not so easy using Biot-Savart law, and it's much easier with Ampere's law. And in at least the version of Physics 1b that I taught, we did Ampere's law for a number of situations. Another simple one is to find the field inside a solenoid. That's very easy to do because in a solenoid the field is uniform, and we know that there's no contribution. If we take an Amperean loop, say like this, there's no contribution from these 3 pieces. The only contribution comes from this path that's parallel to the field in the middle of the solenoid. And it's very easy. We could work out the magnetic field in an ideal solenoid. What we mean by ideal is that the solenoid is much, much longer than its diameter. I think in my version of Physics 1b, we also worked out the B field inside a toroid. That's not much harder than a solenoid. And then that sort of, well, there's a few situations that are symmetric enough to use Ampere's law that are interesting, and I think that about covers it. So we also talked about, so this is kind of backing up to something we did earlier. Remember, we had forces on wires, and if we have wires with currents that are in a magnetic field, there are forces, as we saw a few slides ago, using this formula, and this will allow us to calculate torques on current loops. And we use a very simple example in Physics 1b of a rectangular loop, and that made it easy to calculate the forces by summing these contributions here. And we showed, similar to for electric dipoles, that we could define a so-called magnetic dipole moment that we named as mu, which is a little bit confusing because we use mu for other things. So we used mu naught for the magnetic permeability, but here we have mu vector, and it's and if you remember from Physics 1b, it has a direction which is normal to this loop, and it has a magnitude I. Here I is the current. I was using the notation from the textbook in Physics 1b, which uses little I, which is a little bit annoying, but that's the notation in that textbook. Griffiths uses capital I usually for this, so there's no confusion. But remember, the magnetic dipole moment has units of current times area. And with this in mind, you could always write the torque on a current loop as mu cross with B. Sorry, I'm missing a little arrow here. I should have an arrow on it, which is just this magnetic dipole moment. Okay, so that includes the part of magnetostatics, or the part of 1b that's relevant to the first half of this course 2114. In this course, however, we will include another area of magnetostatics that we didn't cover in Physics 1b, and that's magnetic materials. So we'll have to deal with magnetization of materials, and we'll see how that affects or that leads to some interesting new aspects of magnetostatics, that is, magnetic fields when they're in the situation of steady currents. Now, as it turns out, in Physics 1b, we did move on to another topic, and that was to go beyond magnetostatics to situations where we had changing magnetic fields. And that was known in 1b as induction. And in this course, you will get to changing magnetic fields again, but you won't get to that part until the second part of this course, taught by Dr. Rees. Just for the sake of completeness, however, I will, in this introduction, go over the part of 1b that dealt with changing magnetic fields, and in particular the laws of induction. So in Physics 1b, you you studied what is known as Faraday's law, in particular Faraday's law of induction. So Faraday's law of induction describes a type of electromotive force. Well, what's electromotive force? Well, electromotive force is a very old name that arose a long time ago. So it's not really a force. It's kind of the integrated force through a wire or something. So, for example, a battery produces electromotive force, and this is the chemical nature, and this electromotive force of a battery drives a current around a circuit, and you can see that a battery's electromotive force is equivalent to providing a electrostatic potential difference. So electromotive force is not really a force; it's a type of potential difference. You can think of as an integrated force per unit charge, let's say, around some circuit. And so, of course, batteries are the main example of electromotive forces that you're familiar with. But as we discussed in Physics 1b, Faraday discovered another type of, a very novel type of electromotive force, an electromotive force that was induced by changing magnetic fields. And so it's a kind of tangential force per unit charge integrated over the length once around a complete circuit. Well, okay, tangent to what? Well, tangent to some conducting loop or path, right? And as I said, the integrated force per unit charge has the same units as the potential difference, and essentially electromotive force is a type of potential difference or maintains a potential difference, and this potential difference drives currents around the circuit. But for Faraday's type of induction, this electromotive force is not created and maintained by a battery. It just exists around a continuous conducting loop in a bulk conductor or even in free space, as you'll see. And you'll see this in the second part of this course. So Faraday discovered that the magnitude of this electromotive force was given by the so-called flux rule, and that is that this electromotive force, big epsilon, or big E, I guess we should call it, the script E, is the negative time rate of change of the magnetic flux that goes through the loop. So phi sub B, as we'll call it, it's like the electric flux we had before, it's calculated over a surface that's defined by a loop. So if I have a current loop or a wire here that defines a surface, and we can always calculate the flux of the B field in the same manner that we calculated the flux of the E field through a surface. It's just we take the surface to be one that is defined by this wire or path. And we'll see why there's a negative sign here. That comes from Lenz's law, and it gives us a sign of the electromotive force. And if you remember, the sign is such that any resulting current flow opposes the change in flux causing the EMF. So in this diagram here, if I imagine increasing the magnetic field in this direction with time, well, a magnetic field, this would be created by a current flowing counterclockwise here using the right-hand rule. So if I'm increasing the magnetic field, Lenz's law says that the induced EMF is counter to that, right? And in 1b, we looked at a couple of different ways of inducing electromotive force. If we consider this loop, let's make it a square loop for simplicity. The flux in this case, if the magnetic field is perpendicular, imagine the magnetic field makes some angle with this surface, then it's very easy to calculate the flux. It's just the magnitude of the magnetic field times the area times this cosine theta, which comes from the dot product, of course. And the induced EMF would be the time rate of change of this quantity. And of course, we can increase the magnetic field, we could change the area with time, or we could change the angle with time. All of these can give rise to a changing flux and therefore induced EMF. You can also, if you look back at my notes, you'll see where I've explained how this looks even an increasing magnetic field looks like flux cutting across the conductor. I'm not going to go through that now. You can look at my notes if you have 1B notes. The main point is to realize that Faraday's law works whenever there's a changing magnetic flux. And in 1B we looked, well, this is actually from my notes, so if you want to have a look at this, I won't go in detail, but you could understand Lenz's law if you looked at the forces in particular for a circuit here. If you increase the applied B field, you can think of flux crossing across the loop. You can also think of moving a conductor through a magnetic field, and you'll see how the Lorentz force will actually give you an EMF directly from this. So it's not really mysterious. It's just Faraday was able to summarize this in a way that maybe is not so straightforward to see. But really, just the point is, it just comes from the magnetic forces that we already, force law we already understand. And sort of one of the last topics in Physics 1B that was covered was calculating inductance. And the idea with inductance, at least when I teach the course, I start out with mutual inductance, and I consider the situation. Suppose we have two loops, loop 1 here that has some current flowing in this direction, and we're thinking about that the current from loop 1 creates a magnetic field here, and if we change the current in loop 1, we would change the flux of this loop, and therefore we would drive current around this loop. And the idea is to find the electromotive force induced by changing current. So electromotive force in loop 2 that's induced from a change in current in loop 1. And of course, we can work out the details. We can always calculate the B field due to a current in loop 1. Of course, this is just Biot-Savart Law being used. But we also note that the magnitude of the B field is always proportional to the current. And so we could calculate the flux. And in general, I wrote this down when I taught 1B, that the flux in loop 2 due to a current in loop 1 is some rather complicated double integral. We didn't do this in Physics 1B because it's actually complicated, but we could say that it's just this constant of proportionality, this integral. That is, if we take all this integral except for the I, the point is that the B field and the flux is proportional to the current, and this constant of proportionality we call the mutual inductance. So we could sort of lump all this complication into this constant M21, which really just depends on the geometry, and we call this the mutual inductance. And so we could see very easily that the electromotive force in loop 2 is just proportional to the time rate of change of the current in loop 1. Now in Physics 2114, you'll actually introduce some additional concepts, and you'll be able to calculate much more easily be able to calculate mutual inductances and so forth. And you'll do this for a few examples, and that will occur in the second half of this course. So in Physics 1B, we just kind of wrote it down and said in principle we could calculate this, but we didn't really do any examples. And that's because it's difficult, but in this course, using vector calculus, you'll find that you can introduce a so-called vector potential for magnetic fields, and this will allow you to do these types of calculations. Well, we saw in the last slide that changing a current in loop 1 induces an EMF in loop 2, and that it's proportional to the time derivative of the current in loop 1 and vice versa. But you might want to think, well, what if changing a current in loop 1 also changes the flux across the surface defined by loop 1? Does that give an EMF in loop 1 itself? And indeed it does. And this is where you get the concept of self-inductance. And so basically, if you change the current in a loop, it changes the flux, and you'll get an EMF that opposes this change in current, hence the minus sign there. And we usually call that L instead of M, and we call that self-inductance. And so then if you have some number of loops, which is typically what we call an inductor, you can specify it by its self-inductance L, and this usually comes with this symbol. And in 1b, you would have calculated the self-inductance of a few examples. In particular, for a long solenoid, it's quite easy to do. I'm not going to go through this calculation. You should really know this for this course. So if you don't remember it, or if you don't know it, have a look at it again. The key is you know what the magnetic field is for a solenoid, then you know what the flux is, and you can calculate the induced EMF, and then you can sort of just read off in this simple example what the self-inductance is. In 1b, if you took my course 1b for a problem or even in class, I also calculated the self-inductance of a long coaxial cable. That's a situation where you have current running up some long inner conductor and flowing back down some outer conductor, and this is a little bit more complicated to calculate the self-inductance, more complicated than the solenoid, but it's pretty straightforward as well. You just have to find the proper loop, and you're interested in the EMF around this loop, so you need to define, you need to calculate the flux in between the two conductors, and of course it's not constant, so it's a little bit more complicated, and you'll have to do an integral, and you'll be able to calculate the self-inductance of a long coaxial cable. This I also recommend you go through, but like I said, you won't get to this until part 2 of the course, so you won't have to worry about this for my part, but it's also something I think you should know before you head into the second half of this course. Well, finally, back in 1b, by considering building up a current in an inductor and how that has a back EMF, you have to do work to build up a current in a conductor. We are able to determine, much like we did for parallel plate capacitor, that you can store energy in an inductor, and this energy, it can be written in terms of the current and the inductance, but also in general, you will find that you can write this in terms, at least for the solenoid, you could write this in terms of the magnetic field, and we did that in 1b. Now what you'll see in this course, and in particular in the second half, is that there's energy. Whenever you have a magnetic field, there's an energy density stored in the magnetic field, and it has this form b squared over 2 mu naught. And just similar to what we'll find in the first part of this course, that for electric fields, there's an energy density 1/2 epsilon naught magnitude of E squared. Okay, so that was really that's it for the review of Physics 1b, and I realize some of you will be fresh out of 1b from term 1, and maybe this is a little bit of repetition. Sorry about that, but I think it's good for you to, before you start this course, is to really go over Physics 1b. Make sure you understand the content of that course, and you'll really be set up for understanding or for doing well in this course, because this course will treat the material, a lot of the same material, but we'll do it from the point of view of vector calculus and in a bit more sophisticated presentation, and we'll learn Maxwell's equations. And so that can be much more mathematical, and it's much more general and much more useful, but it's a little bit more sophisticated. But if you have a good understanding of Physics 1b, you'll have a good picture of the relevant physics, and having a good picture of the physics is really important for when you're trying to do things that are more abstract and more mathematical. At least that's how I work. So I realized that took all of 2 lectures to get through this, but I wanted to make sure everyone is at the same level, and you really go into this course with what you've learned in Physics 1b. And I tried to condense it in a short amount of space and time, and you'll be able to see these notes on the Moodle website. Now, if you want more details, I think most of you will still have access to the notes from Physics 1b. If you don't, ask one of your classmates to help you out with that, and you'll find those notes. You'll also find this material in the first year physics textbooks. You'll find a lot of this material in the Feynman lectures, which you can find online as well, as I mentioned. Okay, so that's it for the review of 1B. In the next lecture, I know most of you have had, well, as a prerequisite, you had to take a vector calculus course. So in the next, I will upload some notes on vector calculus, that is differential and integral vector calculus, try to summarize what you've had until now. I will upload those notes, and the next lecture I will cover a small amount of that. Not the very, very basic stuff, but maybe, let's say, the more advanced stuff that's relevant to this course. Okay then, so we'll see you next time.